Somewhere in our galaxy, right now, there is a dead star spinning hundreds of times every second. It has been doing this for thousands of years, with a regularity so precise it rivals the best atomic clocks ever built by human beings. Scientists can predict its pulses years into the future, down to the microsecond. And then, without any warning, it jumps. In an instant, this object, which weighs more than our entire sun crushed into a ball the size of a city, suddenly spins faster. Not by much, but enough to shatter every prediction. Something deep inside this star, in a place no telescope can see and no instrument can reach, snapped. And what physicists think is happening in there is one of the strangest ideas in all of astrophysics. Before we dive into this, if you find these kinds of deep explorations fascinating, a quick like or subscribe genuinely helps this channel grow. It's a small thing, but it means a lot to me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with a star. Not our star. Not the sun. A much larger star. A star that was born perhaps 20 times more massive than the sun, maybe 25 times. A star that burned furiously bright for millions of years, flooding space with light and radiation. A star that, from its very first moment, was already doomed. Because here's what you need to understand about stars before we can talk about pulsars. Stars aren't eternal. They are not permanent fixtures in the sky. They are born, they live, and they die. And how a star dies depends almost entirely on one thing: how massive it was when it was born. Small stars like our sun live long, quiet lives. They burn steadily for billions of years, and when they finally run out of fuel, they swell into red giants, shed their outer layers gently into space, and leave behind a small, dense ember called a white dwarf. It's a peaceful death. Slow, dignified, quiet. But massive stars, stars many times heavier than our sun, don't get a peaceful death. They get something violent, something catastrophic, something so powerful that for a brief moment, a single dying star can outshine an entire galaxy containing hundreds of billions of other stars. And what that explosion leaves behind is one of the strangest and most extreme objects in the entire universe. Let me walk you through exactly how this happens, because every detail matters for understanding what a pulsar is. A massive star spends most of its life fusing hydrogen into helium in its core. This is what all stars do. Hydrogen is the fuel, and the star's core is the furnace. The temperatures at the center of a massive star reach tens of millions of degrees, hot enough to force hydrogen nuclei together, despite the fact that they naturally repel each other. When they fuse, they release energy. That energy pushes outward as radiation pressure, and it's this outward push that holds the star up against the relentless inward pull of its own gravity. The star exists in a delicate balance. Gravity wants to crush it. Radiation pressure wants to blow it apart. And for millions of years, these two forces hold each other in check. The star is stable, but fusion produces a byproduct. When hydrogen fuses, it creates helium. Over millions of years, helium accumulates in the core like ash building up in a fireplace. Eventually, the hydrogen in the core runs out. There's nothing left to fuse. Without fusion, there's no outward radiation pressure. Gravity begins to win. The core starts to contract. But here's the thing about massive stars. They're so heavy and so hot that when the core contracts and heats up further, it reaches temperatures high enough to start fusing helium into carbon. This requires temperatures of about 100 million degrees. For a star the mass of our Sun, this transition is dramatic, but for a truly massive star, 20 or 25 times the Sun's mass, it's just the next step in a process that's going to repeat itself again and again. Because once the helium runs out, the core contracts again. Temperatures rise further, and carbon begins fusing into neon. Then neon fuses into oxygen. Then oxygen fuses into silicon. Each time, the star squeezes its core tighter, raises the temperature higher, and begins burning a new fuel. Each new fuel produces a heavier element. The star develops a layered structure, like an onion. Hydrogen burning in the outermost shell, helium beneath that, carbon beneath that, neon, oxygen, silicon, each in its own shell, each producing the fuel for the layer below. It's an extraordinary structure, layers upon layers of nuclear furnaces, all nested inside one another, all burning different elements at different temperatures, all fighting gravity. But this process has a limit, and that limit is iron 56. When silicon fuses in the core, it produces iron, and iron is where everything stops. Every element lighter than iron releases energy when it fuses. That's what powers the star. But iron is different. Iron sits at the peak of nuclear stability among the elements that stellar fusion can actually produce. Fusing iron doesn't release energy, it absorbs energy. It takes energy away from the star instead of giving it. So when the core fills up with iron, fusion stops. There's no more fuel. There's no more outward pressure. The furnace goes dark. And now gravity, which has been waiting patiently for millions of years, held at bay by the energy of fusion, finally has nothing opposing it. What happens next takes less than a second. The iron core collapses, not slowly, not gradually. It collapses at speeds approaching a quarter of the speed of light. The core, which might be roughly the size of Earth, containing about 1.5 times the mass of the Sun, falls inward on itself in a fraction of a second. Think about what that means. A ball of iron as wide as our planet, containing more mass than the entire Sun, compressing itself down to something about 12 miles across in less than 1 second. The speeds involved are staggering. Material from the outer parts of the core is falling inward at roughly 70,000 kilometers per second. That's about 23% of the speed of light. Nothing in your everyday experience can prepare you for what this kind of collapse means physically. As the core collapses, the density rises astronomically. At normal densities, matter is mostly empty space. Atoms have vast distances between the nucleus and the electrons relative to the size of the nucleus itself. But under this kind of pressure, atoms are crushed. Electrons are forced into the protons. They merge, forming neutrons and releasing a flood of ghostly particles called neutrinos. The matter that was once iron, once made of distinct atoms with electrons orbiting nuclei, becomes a sea of neutrons packed together so tightly that the entire core is essentially one enormous atomic nucleus. This is not a metaphor. This is literally what happens. The core becomes nuclear matter. The density reaches somewhere around 100 trillion times the density of water. A single teaspoon of this material would weigh roughly 4 billion tons on Earth. If you could somehow scoop out a teaspoon of neutron star material and place it on the surface of our planet, it would weigh more than every single car, truck, building, and ship on Earth combined. And we're talking about a teaspoon, a volume smaller than your thumbnail. The collapse doesn't continue forever, though. When the core reaches nuclear density, the neutrons resist being compressed any further. There's a quantum mechanical effect called neutron degeneracy pressure, related to a principle discovered by physicist Wolfgang Pauli that says neutrons cannot all occupy the same quantum state. They push back. The core suddenly stiffens. It becomes incompressible, and the infalling material slams into this newly rigid core like a truck hitting a concrete wall at 70,000 kilometers per second. The core bounces, a shockwave forms, and that shockwave, powered by the enormous energy of the collapse and boosted by the flood of neutrinos pouring out of the core, tears through the outer layers of the star and blows them into space. This is a supernova. Specifically, this is what astronomers call a core collapse supernova, or a type 2 supernova. And it is one of the most violent events in the known universe. For a few weeks, the exploding star can shine with the brightness of several billion suns. Several billion. That's a significant fraction of the light output of an entire galaxy. A single star, in its death, outshining the combined light of hundreds of billions of other stars. If a supernova occurred at the distance of the nearest star to our solar system, about 4 light years away, it would be visible during the day. It would cast shadows at night. It would be one of the most dramatic events any human being has ever witnessed. In the year 1054, Chinese astronomers recorded a guest star that appeared in the sky and was visible in broad daylight for 23 days. That guest star was a supernova, and the remnant of that explosion is what we now call the Crab Nebula, a cloud of expanding gas about 11 light years across, still glowing nearly 1,000 years later. And sitting right at the center of that cloud, spinning 30 times every second, is one of the most studied objects in modern astrophysics. A pulsar. But we'll come back to that. First, you need to understand exactly what's left behind when the explosion is over. Because the outer layers of the star, the hydrogen, the helium, the carbon and oxygen and silicon, all of that gets blasted into space. It expands outward at thousands of kilometers per second, eventually forming a beautiful nebula, a cloud of enriched gas that will one day collapse to form new stars and new planets. But the core stays behind. That ball of neutrons, 12 miles across, containing more mass than our sun, stays right where it is. This is a neutron star, and a neutron star is unlike anything else in the universe. Let me try to give you a sense of what this object is like, because the numbers alone don't capture it. You need to feel the extremes. Imagine taking our sun, a star 864,000 miles across, and crushing it down until it fits inside a city. Not a country, not a state, a city. The entire mass of the sun compressed into a sphere about 12 miles in diameter. That's roughly the distance you might drive across a medium-sized town. The object that results from this compression is so dense that the gravity on its surface is about 200 billion times stronger than the gravity on Earth's surface. If you could somehow stand on the surface of a neutron star, which you absolutely could not because you'd be instantly crushed into a thin film of atoms, but if you could, you would weigh about 28 trillion pounds. A marshmallow dropped onto a neutron star's surface would hit with the energy of a nuclear bomb. Not because the marshmallow is special, but because the gravity is that intense. Objects falling onto a neutron star accelerate to roughly half the speed of light before impact. The surface gravity is so extreme that the tallest mountain on a neutron star is estimated to be about 1 millimeter high, maybe 2 millimeters at most. The gravity flattens everything. No bumps, no hills, no ridges taller than a fraction of an inch across the entire surface. Now, Here's where things get really interesting. When the core of that massive star collapsed, something happened that physics demands but that your intuition might struggle with. The star sped up, dramatically. Think of an ice skater doing a spin. When the skater pulls her arms in close to her body, she spins faster. She hasn't added any energy. She hasn't pushed off anything. She simply moved her mass closer to her axis of rotation, and the laws of physics did the rest. This is called conservation of angular momentum. It's one of the most fundamental principles in all of physics. The total angular momentum of a rotating system stays constant unless an outside force acts on it. If the radius shrinks, the rotation speed increases to compensate. Now apply this to a collapsing stellar core. The original star might have been rotating once every few weeks. That's slow. You wouldn't even notice it. But when that star's core collapses from something the size of Earth down to something 12 miles across, the radius shrinks by a factor of roughly 600. The conservation of angular momentum means the rotation speed increases enormously. What was once a lazy spin of maybe once every 30 days becomes a furious rotation of many times per second. Some neutron stars, at the moment of their birth, are spinning dozens of times per second. The fastest known neutron stars, the millisecond pulsars, spin hundreds of times per second. Think about that. An object more massive than the Sun, 12 miles across, completing a full rotation in a few milliseconds. The surface at the equator of such an object is moving at a significant fraction of the speed of light. It's almost inconceivable. A city-sized ball of matter, heavier than the Sun, whipping around so fast that if you were somehow watching it, the rotation would be a blur far too fast for your eye to track. But spinning fast isn't enough to make a pulsar. Lots of things spin. What makes a pulsar special is what it does with its magnetic field. When the original star collapsed, the same principle that sped up its rotation also intensified its magnetic field. Magnetic field lines get compressed along with the matter. A star that might have had a magnetic field similar in strength to our sun's ends up with a magnetic field that's been amplified by a factor of roughly 1 billion or more. The magnetic field of a typical neutron star is about 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields 1,000 times stronger than that. These are the most powerful magnetic fields known to exist anywhere in the universe. This intense magnetic field does something remarkable. It channels charged particles, electrons and positrons, along the magnetic poles. These particles are accelerated to nearly the speed of light by the enormous electromagnetic forces near the neutron star's surface. As they stream outward along the magnetic field lines, they emit beams of radiation. Radio waves, X-rays, gamma rays, depending on the energy of the particles and the strength of the field. These beams shoot out from the magnetic poles of the neutron star, like two lighthouse beams, narrow and intense, punching through space in opposite directions. Now here's the crucial detail. The magnetic poles of a neutron star are usually not aligned with a rotation axis. Think about Earth. Earth's geographic north pole, the point around which the planet rotates, is not in the same location as Earth's magnetic north pole. They're offset by several degrees. The same is true for neutron stars, except often the misalignment is much more dramatic. The magnetic axis might be tilted 30 degrees, 45 degrees, even 90 degrees from the rotation axis. This means that as the neutron star spins, Those beams of radiation sweep through space like the beams of a lighthouse rotating on a cliff. If you happen to be in the path of one of those beams, you see a pulse of radiation every time the beam sweeps past you. One pulse per rotation. The star spins, the beam sweeps, you see a flash. Spin, sweep, flash, over and over with extraordinary regularity. This is a pulsar. The name is short for pulsating star, though the star itself isn't actually pulsating. It's rotating. The pulses are a geometric effect. You're seeing the beam only when it points at you. Between pulses, the beam is pointing somewhere else. The star hasn't stopped emitting. You just can't see it for that fraction of a second. Pulsars were discovered in 1967 by Jocelyn Bell Burnell, a graduate student at Cambridge University working under astronomer Anthony Hewish. Bell Burnell was analysing data from a radio telescope designed to study a completely different phenomenon: the twinkling of distant radio sources caused by the solar wind. But in the data, she found something strange. A series of regular, repeating radio pulses coming from a fixed point in the sky. The pulses arrived every 1.337 seconds, with astonishing regularity. Nothing natural was known to produce such precise, clock-like signals. For a brief period, the team half seriously considered whether they might be receiving signals from an extraterrestrial civilization. They even nicknamed the source LGM-1, short for Little Green Men 1. But when Bell Burnell found a second pulsing source in a completely different part of the sky, and then a third, the extraterrestrial hypothesis faded. It seemed unlikely that multiple alien civilizations in different parts of the galaxy would all be broadcasting with the same kind of signal. The explanation had to be natural. What Bell Burnell had discovered was pulsars, rapidly rotating neutron stars sweeping beams of radio waves across the cosmos. It was one of the most important astronomical discoveries of the 20th century. The discovery deserves a moment because the human story behind it is extraordinary. Bell Burnell was a 24-year-old graduate student. She had spent the better part of 2 years helping to build the radio telescope by hand, stringing more than 1,000 wooden posts across a field and connecting them with cables and wire mesh. The telescope covered an area of about 4.5 acres. It looked less like a sophisticated scientific instrument and more like a farmer's fence gone horribly wrong. But it worked. It picked up radio signals from the sky and recorded them on rolls of chart paper that Bell Burnell analyzed by hand, running through roughly 100 feet of paper every day. Night after night, she studied the squiggles and blips on those charts, learning to distinguish between real signals and interference from cars, electric fences, and television sets. This signal that would change everything showed up as a tiny scruff on the paper, a bit of what she called scruff. It didn't look like much. A few small, evenly spaced blips. Most people would have dismissed it as interference, but Bell Burnell had developed an eye for the data. She noticed that the scruff kept appearing at the same position in the sky, which meant it wasn't coming from a terrestrial source. Interference from human technology would move with the ground, but this signal moved with the stars. Something in space was pulsing. When she showed the signal to Hewish, there was genuine uncertainty about what it could be. The regularity was unsettling. Nature tends to produce messy, variable signals. Stars flicker, galaxies rumble with broad, chaotic noise. But that was a clean, precise tick. 1.337 seconds between pulses, repeating without variation. It was almost too perfect to be natural. That's what prompted the half-serious Little Green Men hypothesis. If you were an alien civilization trying to announce your presence, a repeating radio beacon would be exactly the kind of signal you might build. The fact that the team even considered this, even briefly, tells you how strange the discovery was. Nothing in the known universe produced signals like this. It took the discovery of more pulsing sources in different parts of the sky to settle the question. Whatever was making these signals, it was a class of natural objects, not a single artificial transmitter. The explanation, rapidly rotating neutron stars, had actually been predicted theoretically before Bell-Bonnell's discovery. But nobody had expected to actually find them. The theory existed on paper. Bell-Bonnell turned it into reality by paying attention to a bit of scruff that anyone else might have ignored. Today, we know of more than 3,300 pulsars in the Milky Way. They spin at different rates. Some rotate once every few seconds, some once every few milliseconds. Their pulse periods range from about 1.4 milliseconds for the fastest to several seconds for the slowest. Each one is a neutron star, a dead stellar core left behind by a supernova explosion, spinning in the darkness of space, sweeping beams of radiation through the void. Most of them will never be detected because their beams don't happen to point toward Earth. The ones we see are simply the ones whose geometry happens to line up so that the beam crosses our line of sight. For every pulsar we detect, there are probably many more whose beams sweep through parts of the sky where no one is watching. Let me give you a few more details about the physical conditions on and around a neutron star, because these details matter for understanding everything that comes next. The interior of a neutron star is layered. The outermost layer is a thin atmosphere, maybe a few centimeters thick, made of hydrogen or helium or heavier elements, depending on the star's history. Beneath that is a solid crust. Yes, solid. Despite the incredible temperatures, the pressure is so immense that the matter in the outer layers forms a crystalline lattice, similar in structure to a metal on Earth, but made of nuclei far heavier than anything you'd find naturally on our planet. These nuclei are arranged in a rigid grid, held in place by the intense pressure and the electromagnetic forces between them. The crust is only about a mile or so thick, but it is rigid. It's a solid shell surrounding the liquid interior. And that interior is where things get truly exotic. Beneath the crust, the density is so high that matter exists in a state that doesn't occur naturally anywhere else in the universe. The neutrons in the interior form what physicists call a superfluid. A superfluid is a state of matter that has zero viscosity. It flows without any friction whatsoever. If you stirred a superfluid, it would keep spinning forever. It would never slow down on its own. Normal liquids, water, oil, even liquid helium at everyday temperatures, all have some viscosity. They resist motion, drag slows them down, but a superfluid has none of that. It's frictionless in a way that's hard to even imagine. This superfluid state arises because of the enormous densities inside a neutron star. Neutrons pair up through quantum mechanical interactions. These paired neutrons behave collectively as a single quantum system, and that system exhibits superfluidity. It's the same basic physics that allows liquid helium to become a superfluid when cooled to near absolute zero in laboratories on Earth. But inside a neutron star, it's happening at temperatures of hundreds of millions of degrees. It's not cold that creates the superfluid here. It's the extraordinary density. Now, why does this matter? It matters because a superfluid doesn't rotate the way a normal liquid rotates. When you spin a bucket of water, the water rotates as a continuous fluid. Every part of the water participates in the rotation, but a superfluid can't do that. Quantum mechanics forbids it from rotating as a uniform body. Instead, a rotating superfluid forms tiny thread-like structures called quantized vortices. Each vortex carries a specific, fixed amount of angular momentum. The faster the superfluid needs to rotate, the more vortices it creates. A neutron star's interior might contain billions upon billions of these vortices, each one a microscopic thread of rotating superfluid, all arranged in a vast array throughout the star's interior. And here's the critical point. These vortices interact with the solid crust above them. They can become pinned to the crystal lattice of the crust, stuck in place by nuclear forces. When a vortex is pinned, it can't move freely. It's anchored to the crust. And this pinning, this interaction between the superfluid interior and the solid crust, is at the heart of what causes a pulsar glitch. But we're getting ahead of ourselves. Before we can understand glitches, we first need to understand just how stable pulsars normally are. Because the glitch only makes sense when you appreciate how perfectly, how impossibly regular a pulsar's rotation usually is. The precision of these cosmic clocks is something that will genuinely astonish you. And that regularity, that almost supernatural steadiness, is what makes the sudden jump of a glitch so shocking and so scientifically valuable. Right now, across the Milky Way, thousands of neutron stars are spinning in the darkness. Each one is a remnant of a star that died violently, its core crushed to nuclear density, its rotation accelerated to dizzying speed, its magnetic field amplified to almost incomprehensible strength. Each one is sweeping beams of radiation through space like a cosmic lighthouse, and each one is ticking away, pulse after pulse after pulse, with a regularity that seems almost impossible for a natural object. These are the pulsars, dead stars that refuse to be silent. And understanding what they are, understanding the physics that created them, and the forces that govern them, is the foundation for everything that comes next. Because something is happening inside these stars, something deep beneath the crust, in the superfluid darkness of the interior, where the laws of quantum mechanics govern matter at densities we cannot reproduce in any laboratory. And every once in a while, that something makes itself known in the most dramatic way possible. The star jumps. So now you know what a pulsar is: a dead star, a neutron star, a ball of matter more massive than the sun, crushed down to the size of a city, spinning at extraordinary speed, sweeping beams of radiation through space like a lighthouse on the edge of eternity. But knowing what a pulsar is only gets you halfway to understanding why a glitch is so shocking. Because to appreciate the glitch, you need to understand the one thing about pulsars that makes them unlike almost anything else in nature: their stability, their almost supernatural precision. The fact that a pulsar, once you account for a slow and predictable fading of its rotation, ticks with a regularity so exact that it rivals the best timekeeping devices human beings have ever constructed. And in some cases, it surpasses them. Let me explain what I mean by that, because the numbers here are genuinely astonishing. When a radio telescope detects a pulsar, what it actually picks up is a repeating pattern of radio waves. Every time the pulsar's beam sweeps across Earth, the telescope records a brief spike in signal, then silence, then another spike, then silence, over and over. Spike, silence, spike, silence. The time between each spike is the pulse period, and it corresponds to exactly one rotation of the neutron star. If the pulsar rotates once every 33 milliseconds, then you get a pulse every 33 milliseconds. If it rotates once every 1.3 seconds, you get a pulse every 1.3 seconds. The pulse period is the rotation period. They are the same thing. Now, you might think that measuring the time between pulses to high accuracy would be difficult. Radio waves from space are faint. The signals are noisy. The interstellar medium, the thin gas between stars, distorts and delays the radio waves as they travel toward Earth. Earth's own atmosphere adds more noise. The telescope itself introduces measurement errors. And yet, despite all these sources of uncertainty, astronomers can measure pulsar periods with precision that borders on the absurd. Here's how they do it. They don't just measure one pulse, they measure millions of them. They observe a pulsar for hours, days, weeks, months, years, accumulating vast numbers of individual pulses. Each individual pulse might be slightly noisy, slightly variable in shape and intensity. That's normal. Individual pulses from a pulsar are not perfectly identical. Some are bright, some are dim. Some arrive with slightly different shapes. The emission process that creates each individual pulse involves complex physics in the magnetosphere of the neutron star, and this introduces variability from pulse to pulse. But here's the key insight. Even though individual pulses vary, the average behavior over many pulses is extraordinarily stable. When you fold thousands or millions of pulses on top of each other, aligning them by the pulse period, the random variations cancel out and what remains is a precise, repeating pattern. The average pulse profile, the shape of the signal when you add up thousands of pulses, is remarkably consistent. It's like a fingerprint. Each pulsar has its own unique average profile, and that profile stays the same year after year after year. Using this technique of folding and averaging, astronomers build what they call a timing model. A timing model is a mathematical description of exactly when every single pulse from a pulsar should arrive at the telescope. It accounts for the pulsar's rotation rate, the rate at which that rotation is slowing down, the pulsar's position in the sky, its distance, its motion through space, Earth's motion around the sun, the effects of the interstellar medium on the signal, even the gravitational influence of any companion stars if the pulsar happens to be in a binary system. The timing model predicts when each pulse will arrive. And then the astronomer compares the prediction to reality. The agreement is stunning. For the best time pulsars, the timing model can predict the arrival time of a pulse years into the future with an accuracy of a few microseconds. A microsecond is 1/1,000,000th of a second. Think about that. An astronomer can tell you years in advance exactly when a pulse from a neutron star, hundreds or thousands of light years away, will arrive at a radio telescope on Earth and be correct to within a few millionths of a second. That's like predicting exactly what time a train will arrive at a station 3 years from now and being off by less than the time it takes light to travel half a mile. Some millisecond pulsars, the fastest spinning ones, are even better than this. These are pulsars that spin hundreds of times per second, completing a full rotation in just a few milliseconds. They are old neutron stars that have been spun up by accreting matter from a companion star. The infalling matter carries angular momentum, which speeds up the neutron star's rotation over millions of years until it's spinning at fantastic rates. These millisecond pulsars have extremely stable rotation rates. The best of them can be timed with a precision of tens of nanoseconds over a period of years. A nanosecond is 1 billionth of a second. The time it takes light to travel about 1 foot. That's the level of precision we're talking about. A dead star spinning in the void of space, keeping time to within billionths of a second. Let me put this in a context that might mean more to you. The most accurate clocks on Earth are optical lattice clocks, a type of atomic clock that uses the vibrations of atoms trapped in a lattice of laser light to define the passage of time. These clocks are accurate to about 1 second in 30 billion years. That's extraordinary. It means if you started one of these clocks at the Big Bang and let it run for the entire age of the universe, 13.8 billion years, it would have drifted by less than half a second. No human technology has ever kept time this precisely. Now, pulsars are not quite this good. The best millisecond pulsars are stable to roughly 1 part in 10 to the 15 over timescales of years. That's comparable to the performance of the cesium atomic clocks that were the gold standard of timekeeping for decades. The millisecond pulsar PESRB 1937 plus 21, discovered in 1982, was the first millisecond pulsar ever found. It rotates 642 times per second. When it was discovered, its rotational stability was comparable to the best atomic clocks available at the time. A dead star, billions of years old, drifting through the galaxy, was keeping time as accurately as the most sophisticated technology human civilization had ever produced. This comparison is worth sitting with for a moment. An atomic clock is a triumph of engineering. It requires precisely controlled lasers, vacuum chambers, electronics, and a deep understanding of quantum mechanics. It has to be carefully shielded from temperature variations, vibrations, and electromagnetic interference. It represents the pinnacle of human ingenuity applied to the problem of measuring time. A pulsar is a ball of dead matter left behind by a stellar explosion. It has no moving parts in any conventional sense, no electronics, no engineering. It's just a lump of neutrons spinning in the vacuum of space. And it keeps time almost as well as our best clocks. That fact alone should tell you something profound about the physics governing these objects. So, why are pulsars so stable? What is it about a neutron star that makes its rotation so incredibly regular? The answer comes down to one concept: moment of inertia. The moment of inertia is a measure of how much an object resists changes to its rotation. It depends on two things: the object's mass and how that mass is distributed relative to the axis of rotation. A figure skater with her arms extended has a large moment of inertia and spins slowly. The same skater with her arms pulled in has a smaller moment of inertia and spins faster. But the total angular momentum stays the same. Now, a neutron star has an enormous moment of inertia. Not because it's physically large, it's only about 12 miles across, but because it's extraordinarily massive. A typical neutron star contains about 1.4 times the mass of the Sun, roughly 2.8 times 10 to the 30 kilograms. That's an almost incomprehensible amount of mass. And all of it is concentrated in a very compact, very dense sphere. The result is a moment of inertia of roughly 10 to the 45 kilogram meters squared. This is an abstract number, so let me explain what it means in practical terms. It means the neutron star is like a cosmic flywheel. A flywheel is a heavy, spinning disk used in engines and machines to smooth out fluctuations in rotation. The heavier the flywheel, the more it resists changes to its speed. A light flywheel can be sped up or slowed down easily. A heavy one barely notices small disturbances. It just keeps spinning at the same rate, absorbing any bumps or jolts without changing its rotation perceptibly. A neutron star is the ultimate flywheel. Its moment of inertia is so enormous that tiny forces barely affect it. To change the rotation rate of a neutron star by even a small amount, you need to apply a tremendous amount of torque over a long period of time. Random fluctuations, small asymmetries, minor disturbances, none of these are strong enough to noticeably alter the spin. The star just keeps rotating, pulse after pulse after pulse, with mechanical regularity. This is fundamentally different from most rotating objects in everyday life. A spinning top on a table slows down quickly because of friction with the surface and air resistance. A wheel on a car slows down because of friction in the bearings and the road. Even a satellite in orbit, which is in a vacuum and has no air resistance, can be affected by slight gravitational variations, solar radiation pressure, or magnetic interactions with Earth's field. But a neutron star in open space has almost nothing acting on it. There's no friction, there's no air, there's no surface to drag against. It's spinning in an almost perfect vacuum, and it has the mass of a star concentrated into a volume the size of a city, giving it an immense rotational inertia that makes it incredibly resistant to any perturbation. The result is a rotation rate that stays almost perfectly constant over human timescales. Almost, but not quite. Because pulsars do slow down, every pulsar, without exception, is gradually losing rotational energy. The spin rate is decreasing over time, but it decreases so slowly and so smoothly that it only reinforces how stable these objects are. The slowdown happens because of the pulsar's magnetic field. Remember, a pulsar has a magnetic field roughly 1 trillion times stronger than Earth's, and this field is tilted relative to the rotation axis. As the neutron star rotates, this tilted magnetic field sweeps through space, and the changing magnetic field generates electromagnetic radiation. This is called magnetic dipole radiation. Energy radiates away from the star, carried by electromagnetic waves propagating outward at the speed of light. That energy has to come from somewhere, and it comes from the star's rotational energy. Every bit of electromagnetic energy the pulsar radiates is energy taken from its spin. The star slows down. This process is called spin down, and it's extraordinarily predictable. The rate at which a pulsar slows down depends on the strength of its magnetic field and the current rotation rate. Astronomers characterize it with a quantity called the period derivative, usually written as p dot. P dot tells you how much the period increases per second. For a typical young pulsar, p dot might be something like 10 to the minus 15 seconds per second. That means every second, the pulse period gets longer by about a quadrillionth of a second. That's an almost unimaginably tiny change. If the pulsar has a period of 1 second, it would take roughly 30 million years for the period to increase by 1 second. The slowdown is real, but it's glacial. For millisecond pulsars, the spin down is even slower. Their magnetic fields are weaker, typically 1 billion times weaker than a young pulsar's field, so they radiate much less energy. Their periods change by perhaps 10 to the minus 20 seconds per second. At that rate, the period would take billions of years to change significantly. These old, fast-spinning pulsars are the most stable rotators we know of in the natural universe. They'll keep spinning at nearly the same rate for longer than the current age of the universe. Here's what makes the spin down so important for our story. It's smooth, it's continuous, it's predictable. When astronomers build their timing models, they include the spin down rate as one of the parameters. They measure the current period, the current rate of change of the period, sometimes even the rate of change of the rate of change, and they use these numbers to project forward in time. And the projections work. The predictions match reality to extraordinary precision. The pulsar slows down exactly as the model says it will, pulse after pulse, day after day, year after year. No surprises, no sudden changes, just a slow, steady, predictable deceleration so smooth it's like watching a flywheel the size of a planet coast to a halt over billions of years. To appreciate just how reliable this is, consider the Crab Pulsar, the neutron star sitting at the center of the Crab Nebula. This pulsar, designated PSRB 0531 plus 21, was born in the supernova observed in 1054. It rotates about 30 times per second and is slowing down at a rate of about 36.4 nanoseconds per day. Every single day, its pulse period gets about 36 nanoseconds longer. That might sound like a lot compared to the millisecond pulsars we discussed, and it is. The Crab pulsar is young and has a very strong magnetic field, so it's losing energy relatively quickly. But the key point is that this spin down is smooth and predictable. Astronomers can model it with high precision. They know exactly how fast the Crab pulsar will be spinning tomorrow, next week, next month, next year. They can predict its pulse arrival times far into the future with extraordinary accuracy. Now, you might ask how we actually detect these signals in the first place. The radio waves from pulsars are faint, incredibly faint. By the time they've crossed dozens or hundreds of light years of space and arrived at Earth, the signals are billions of times weaker than the signal from a typical cell phone. Detecting them requires enormous radio telescopes and sophisticated signal processing. The telescopes used for pulsar observations are some of the largest structures ever built. The Parkes Radio Telescope in Australia, a dish 64 meters across, has been one of the workhorses of pulsar astronomy for decades. The Jodrell Bank Observatory in England uses the Lovell Telescope, a 76-meter dish. The now collapsed Arecibo Observatory in Puerto Rico had a fixed dish 305 meters across, one of the most sensitive radio telescopes ever built, and it was instrumental in discovering some of the most important pulsars we know. The 500-meter aperture spherical telescope, known as FAST in China, is currently the largest single-dish radio telescope in the world, and it is discovering new pulsars at an unprecedented rate. These telescopes collect radio waves from space, amplify the signal, and feed it into digital receivers that record the data at high time resolution. The raw data is essentially a stream of numbers representing the intensity of the radio signal over time. Buried in that stream, hidden beneath layers of noise from the sky, from the telescope, from the electronics, is the faint repeating signal of the pulsar. Finding it is like trying to hear a specific heartbeat in a stadium full of screaming fans. You can't hear it in any individual moment. The noise is too loud. But if you know the rhythm, if you know how often the heartbeat occurs, you can fold the data. You take the stream of numbers, chop it into segments exactly one pulse period long, and stack those segments on top of each other. The noise, being random, cancels out when you add enough segments together. The pulse, being regular, adds up. It emerges from the noise like a signal rising above static. The more data you fold, the clearer the pulse becomes. Hours of data, folded at the correct period, can reveal a pulse that's completely invisible in any individual rotation. Once you've detected the pulse and measured its period, you start building the timing model. You measure the pulse arrival times with the highest precision possible, usually by cross-correlating the observed pulse profile with a template, the known average shape of the pulse for that particular pulsar. This gives you a precise timestamp for each pulse, not each individual rotation necessarily, but each observation session produces a set of high precision arrival times. Over weeks, months, and years, you accumulate a database of these arrival times. Then you fit a mathematical model to them. The model includes the pulsar's sky position, its proper motion across the sky, its distance, its rotation period, the rate at which that period is changing, and sometimes higher order derivatives of the period. If the pulsar is in a binary system, the model also includes the orbital parameters, 5 additional numbers describing the orbit's size, shape, orientation, and period. The fitting process is iterative. You start with approximate values, compare the model's predictions to the actual arrival times, adjust the parameters to minimize the differences, and repeat. When you're done, you have a timing model that accounts for every pulse, every single one, across years of data. And the differences between the model's predictions and the actual arrival times, called the timing residuals, are tiny. For the best timed pulsars, the root mean square of the residuals is a few hundred nanoseconds or less. Everything the pulsar does is accounted for. Every rotation predicted, every pulse anticipated. This level of precision has practical consequences that go far beyond just studying pulsars. Astronomers are currently using arrays of millisecond pulsars, networks of the most stable pulsars distributed across the sky, as a galaxy-scale gravitational wave detector. The idea is elegant. Gravitational waves, ripples in the fabric of space-time predicted by Einstein and first directly detected in 2015, stretch and compress space as they pass. If a gravitational wave passes between Earth and a pulsar, it changes the distance very slightly, which changes the pulse arrival time by a tiny amount. By monitoring dozens of millisecond pulsars simultaneously and looking for correlated changes in their timing residuals, astronomers can search for gravitational waves with wavelengths of light years, waves far too long for ground-based detectors to sense. These are waves produced by pairs of supermassive black holes orbiting each other in the centers of merging galaxies. In 2023, several pulsar timing array collaborations around the world announced evidence for exactly this kind of gravitational wave background. A low hum of space-time vibrations pervading the universe, detected not by lasers or mirrors, but by dead stars spinning in the void. Pulsars are so stable, so precise, so reliable, that we can use them as the arms of a gravitational wave detector spanning the entire galaxy. This is the context you need for understanding what comes next. Because everything I've just described, the extraordinary precision, the stability, the predictability, the timing models that account for every pulse across years, all of this paints a picture of an object that is the very definition of regularity. A cosmic metronome, a clock that ticks with inhuman precision, slowing down so gradually and so smoothly that the slowdown itself becomes just another predictable parameter in the model. Nothing about these objects suggests sudden change. Nothing about them hints at surprises. When you study pulsars, you develop an expectation of perfect behavior. You expect the timing residuals to be flat, featureless, boring. You expect the pulsar to do exactly what the model says it will do, pulse after pulse, year after year. The pulsar is supposed to be predictable, it's supposed to be stable. That's the whole point. And then, one day, It isn't. You're looking at the timing residuals and something is wrong. The pulses are arriving too early, not by much. We're talking about microseconds. But the timing model, which has been accurate to within nanoseconds for years, is suddenly off. The pulses period has changed. Not in the smooth, gradual way of spin down, not in the predictable way that the model accounts for. It has changed abruptly. The rotation rate has jumped. The star is suddenly spinning faster than it was a moment ago. There was no warning, no precursor signal, no gradual build-up that you could have used to predict it. One moment, the pulsar was behaving exactly as expected. The next moment, it wasn't. Something happened inside that neutron star. Something deep below the crust, in the superfluid interior, in a place no telescope can reach and no probe can visit. Something shifted. Angular momentum that had been stored somewhere inside the star was suddenly released. The crust sped up. The pulse period got shorter. The timing residuals jumped. This is a glitch. And when you've spent months or years watching a pulsar tick with the precision of an atomic clock, when you've grown accustomed to residuals that are flat and featureless, when you've internalized the expectation that these objects are the most predictable rotators in the natural universe, a glitch is shocking. It's like a perfectly running clock suddenly skipping a beat. Not stopping, not breaking, just suddenly, inexplicably, running a tiny bit faster than it was a second ago. And you have no idea why. The fact that this happens at all, that an object as massive and stable as a neutron star can suddenly change its rotation rate without any external provocation, tells us something profound. It tells us that the interior of a neutron star is not static. It's not a frozen, inert ball of neutrons sitting passively inside its crust. Something is happening in there. Forces are building, stresses are accumulating, energy is being stored, and periodically, unpredictably, that stored energy is released in a sudden event that alters the star's observable rotation. The surface, the part we can see, is telling us about the interior, the part we can't. Every glitch is a message from inside a dead star, a signal from a place where matter exists at densities we cannot create in any laboratory, where quantum mechanics governs the behavior of fluids made of pure neutrons, where the physics is so extreme that we are still, decades after the first glitch was observed, trying to fully understand what is going on. And that is what makes pulsar glitches one of the most fascinating phenomena in all of astrophysics. Not because the change in rotation is large, it isn't. Not because the glitch is visible to the naked eye, it isn't even close, but because a subtle, tiny jump in the spin rate of a dead star opens a window into physics we cannot access any other way. The glitch is our only direct probe of the interior of a neutron star. The only way we have of testing our theories about what happens to matter when you crush it beyond anything we can replicate on Earth. Every glitch is an experiment conducted by nature at pressures and densities that no human laboratory will ever achieve. And all we have to do is watch, listen to the ticking, and notice when the clock suddenly jumps. The first pulsar glitch was observed in 1969, just 2 years after pulsars themselves were discovered. And it happened in one of the most studied pulsars in the sky, the Vela pulsar. The Vela pulsar, designated PSRB 0833-45, is a young neutron star embedded in the Vela supernova remnant, a cloud of expanding gas in the southern sky about 960 light years from Earth. The supernova that created it exploded roughly 11,000 years ago. By pulsar standards, that makes the Vela pulsar a youngster. It rotates about 11.2 times per second, completing one full revolution every 89 milliseconds. Its pulse period has been measured with exquisite precision, and its spin down rate is well known. It's a textbook pulsar. Bright, well studied, regularly monitored by radio telescopes around the world, particularly by the Parkes telescope in Australia, which has been tracking it for decades. In 1969, astronomers noticed something in the Vela pulsar's timing data that shouldn't have been there. The pulse period had suddenly decreased. Not gradually, the way spin down works in reverse, not as part of some smooth trend. It had jumped. In an instant, the pulsar was spinning faster. The rotation rate had increased by a tiny but unmistakable amount. The timing residuals, which had been flat and well behaved for months, suddenly showed a discontinuity, a step, a break in the pattern. One moment the pulsar was spinning at one rate. The next moment, it was spinning at a slightly faster rate. No warning. No gradual build-up. Just a sudden, abrupt change. This was the first observed pulsar glitch, and it was strange enough that nobody quite knew what to make of it. Let me be very precise about what happened because the details matter. Before the glitch, the Vela pulsar had a rotation frequency, the number of times it spun per second, of approximately 11.2 hertz. After the glitch, the rotation frequency was slightly higher. The change was tiny. The fractional increase in spin rate, the quantity astronomers call delta nu over nu, was about 2.34 times 10 to the minus 6. That's about 2 parts in a million. If the pulsar were a clock ticking once per second, this would be equivalent to the clock suddenly gaining about 2 millionths of a second per tick. That doesn't sound like much. In everyday terms, it's nothing. You'd never notice a clock that gained 2 millionths of a second per tick. It would take days for the error to accumulate to even a fraction of a second. But for a pulsar, for an object whose timing is monitored to microsecond precision, for an object whose behavior is predictable to parts in 10 to the 15, a change of 2 parts in a million is enormous. It's like a clock that has been keeping perfect time for years, suddenly jumping forward, not by a lot, but by enough to shatter the prediction, enough to be unmistakable in the data, enough to demand an explanation. And the Vela pulsar didn't just glitch once, it glitched again, and again, and again. Over the decades since that first observation in 1969, the Vela pulsar has been observed to glitch roughly once every 2 to 3 years. As of the most recent counts, it has undergone more than 20 large glitches, making it one of the most prolific glitching pulsars known. Each glitch follows a broadly similar pattern. The spin rate suddenly increases. Then, over the following days, weeks, and months, the pulsar partially recovers. The spin rate drops back toward its pre-glitch value, but it doesn't recover completely. After the recovery phase, the pulsar is left spinning slightly faster than it would have been if the glitch had never happened. The glitch leaves a permanent mark, a permanent change in the rotation rate that never goes away. Each successive glitch adds another small step up in spin rate, partially recovered, but never fully erased. Let me walk through what this looks like in the data because understanding the anatomy of a glitch is essential. Before the glitch, the pulsar is spinning down steadily. Its rotation frequency is decreasing at a known, predictable rate. If you plot the rotation frequency as a function of time, you see a smooth, gently sloping line. tilting downward as the star loses energy through magnetic dipole radiation. The timing residuals are flat. Everything is as expected. Then the glitch happens. On the plot of rotation frequency versus time, you see a sudden vertical jump. The frequency increases instantaneously, or at least faster than the time resolution of the observations can resolve. One data point is on the smooth downward slope. The next data point, taken perhaps hours or a day later, is above the line. The frequency has jumped up. Immediately after the jump, the recovery begins. The rotation frequency starts to decrease again, faster than the normal spin down rate. It's as if the pulsar is trying to return to where it was before the glitch. Over the following days, a significant fraction of the initial jump is erased. The frequency drops back down, but it doesn't drop all the way. After a few weeks or months, the enhanced spin down settles out and the pulsar resumes its normal, steady spin down rate. But it's now sitting on a slightly higher frequency than the pre-glitch extrapolation would have predicted. That permanent offset is called the persistent shift. And it's a crucial piece of the puzzle because it tells us that whatever caused the glitch didn't just temporarily disturb the star, it permanently transferred angular momentum from one part of the star to another. Now, the Vela pulsar's glitches are large by pulsar standards. A fractional frequency increase of a few parts in a million is at the big end of the scale. But not all glitches are this dramatic. Pulsars show a wide range of glitch sizes. Some are enormous like Velas, others are tiny. The smallest detected glitches have fractional frequency changes of about 10 to the minus 11. That's a change of one part in 100 billion. These microglitches are so small that detecting them requires years of precise timing data and careful statistical analysis. They're right at the edge of what our instruments can measure. It's entirely possible, even likely, that there are glitches even smaller than this happening in pulsars all the time. Too small for us to detect with current technology. Between the extremes of Vela-sized glitches and these barely detectable microevents, there's a continuous distribution. Some pulsars glitch frequently with small events. Others glitch rarely, but dramatically. Some seem to do both. The diversity is striking, and it suggests that the underlying mechanism can operate at many different scales, from tiny adjustments to major upheavals, all within the same basic physical framework. The Crab pulsar provides an interesting contrast to Vela. The Crab pulsar, born from the supernova observed in the year 1054, rotates about 30 times per second, nearly 3 times faster than the Vela pulsar. It also glitches, but its glitches are typically much smaller than Vela's. The Crab pulsar's glitches have fractional frequency changes, typically in the range of 10 to the minus 9 to 10 to the minus 8. That's 1,000 to 100,000 times smaller than a typical Vela glitch. The Crab pulsar glitches more frequently than Vela in some periods, but with smaller individual events. It's like comparing a region that gets frequent small earthquakes to one that gets rare but powerful ones. The physics might be related, but the scale is different. What's particularly interesting about the Crab pulsar's glitches is that they sometimes show a different recovery behavior than Vela's. Some of the Crab's glitches recover almost completely. The spin rate jumps up, then returns almost entirely to the pre-glitch trend. Very little permanent shift is left behind. Other Crab glitches leave a more noticeable, persistent offset. The variation suggests that different glitch events, even in the same pulsar, might involve different amounts of the star's interior or different physical processes at slightly different depths. Let's talk about what sudden really means in this context, because this word carries more weight than you might think. When astronomers say a glitch is sudden, they mean the spin up happens faster than they can measure. And they can measure things pretty fast. Pulsar timing observations typically have time resolution ranging from minutes to hours, depending on the observing setup and the brightness of the pulsar. If a glitch happens between two observations separated by, say, 12 hours, all you know is that the glitch occurred sometime during that 12-hour window. You can't pin it down more precisely than that, but astronomers have tried. They've designed observing campaigns specifically to catch glitches in the act. They've observed pulsars continuously for long stretches, taking data with the highest possible time resolution, hoping that a glitch would happen while they were watching. And occasionally they've gotten lucky. In 2016, a team of astronomers caught a Vela pulsar glitch in real time using the Mount Pleasant Observatory in Tasmania. This was a landmark observation. They were monitoring the Vela pulsar with continuous high time resolution observations when the glitch occurred. The data showed that the rise time of the glitch, the time it took for the spin frequency to jump from its pre-glitch value to its peak post-glitch value, was less than 12.6 seconds. That's an upper limit. The actual rise time might have been even shorter. It might have been a fraction of a second, but the data couldn't resolve anything faster than about 12 seconds. So all we can say with certainty is that the spin-up happened in less than 12 seconds. Probably much less. Think about what that means. An object containing more mass than our sun, an object whose moment of inertia is roughly 10 to the 45 kilogram meters squared, an object that has been spinning at a nearly constant rate for thousands of years, suddenly changes its rotation speed in less than 12 seconds. Whatever mechanism causes the glitch acts fast. It doesn't slowly wind up the star like turning a dial. It snaps. Like a rubber band releasing stored tension. Like a fault line giving way in an earthquake. The change is abrupt. Almost instantaneous. And it involves a change in angular momentum that, while tiny in fractional terms, is enormous in absolute terms. The total angular momentum transferred during a large Vela glitch, while tiny as a fraction of the star's total spin, is enormous in absolute terms, far exceeding the rotational angular momentum of any planet in our solar system. That's a staggering amount of angular momentum to transfer in under 12 seconds. This speed, this suddenness, is one of the strongest constraints on any theory that tries to explain glitches. Whatever is happening inside the neutron star has to be capable of acting very quickly. It has to involve a mechanism that can store angular momentum gradually over months or years, and then release it almost instantaneously. That rules out a lot of possibilities. It points towards something catastrophic, something threshold based, something that builds up slowly and then snaps. Let me give you a broader view of glitching pulsars, because the Vela pulsar and the Crab pulsar, while famous, are far from the only ones. As of recent catalogues, more than 200 pulsars have been observed to glitch. Together, they've produced well over 700 individual glitch events. These pulsars span a wide range of ages, rotation rates, and magnetic field strengths. Most glitching pulsars are young or middle-aged. They tend to have characteristic ages of a few thousand to a few 100,000 years. Very old pulsars, especially millisecond pulsars, rarely glitch. There are a few known exceptions, but as a general rule, glitching is a young pulsar phenomenon. This age dependence is itself a clue. It tells us that whatever causes glitches is related to properties that change as a pulsar ages. Young pulsars have stronger magnetic fields, faster spin down rates, and hotter interiors. They are also thought to have thicker crusts and more active superfluid dynamics. As a pulsar ages and cools, its interior changes. The superfluid properties might evolve. The crust might become more or less rigid. The coupling between the crust and the interior might change. All of these factors could affect how often and how severely a pulsar glitches. There's also a pattern in the glitch sizes. Some pulsars show a bimodal distribution of glitch sizes, meaning they tend to produce either very small glitches or very large glitches, with relatively few in between. The Vela pulsar is a good example of this. Most of its glitches are large, with delta nu over nu values clustered around a few times 10 to the minus 6. The Crab pulsar, by contrast, tends to produce smaller glitches. Other pulsars show a more continuous distribution of sizes. This diversity suggests that the glitch mechanism might operate differently in different pulsars, or that the same basic mechanism can produce different outcomes depending on the star's specific internal conditions. One of the most important observations about glitching pulsars is that the cumulative effect of all the glitches over time can account for a significant fraction of the spin down. Let me explain what this means. Between glitches, the pulsar spins down steadily, losing rotational energy. Each glitch temporarily reverses a tiny bit of that spin down by spinning the star up. If you add up all the spin ups from all the glitches and compare that total to the total spin down, you find that for some pulsars, particularly Vela, the glitches collectively offset roughly 1 to 2% of the spin down. That might not sound like much, but it's an important number because it tells you how much of the star's interior is involved. If the glitches are caused by angular momentum transfer from a superfluid component in the interior to the crust, then the total amount of angular momentum transferred over time constrains how much superfluid is participating. For the Vela pulsar, the numbers suggest that the superfluid component responsible for the glitches contains roughly 1 to several percent of the star's total moment of inertia. That's consistent with the neutron superfluid in the inner crust of the neutron star, the region between the solid outer crust and the liquid core. This is one of the strongest pieces of evidence linking glitches to superfluid behavior in the crust. And it's something that will become even clearer once we understand exactly what's happening physically inside the star. Another important observational feature is what happens to the spin down rate itself during a glitch. It's not just the spin frequency that changes. The spin down rate, the rate at which the pulsar is losing rotational energy, also changes. Typically, immediately after a glitch, the spin down rate increases in magnitude. The pulsar starts slowing down faster than it was before the glitch. This enhanced spin down then gradually relaxes back towards the pre-glitch value over days to months. The timescales of this relaxation vary from pulsar to pulsar and from glitch to glitch. Some components of the recovery happen quickly, over hours or days. Other components take weeks or months. And some glitches produce a change in the spin down rate that never fully recovers, leaving a permanent shift in how fast the pulsar is slowing down. These recovery timescales are crucial because they tell us about the coupling between different components of the neutron star's interior. If the recovery is fast, it means the component that transferred the angular momentum recouples quickly to the crust. If the recovery is slow, the recoupling takes longer. Different timescales suggest different physical regions or different types of superfluid are involved. By analyzing the recovery curves in detail, Fitting them with exponential decay functions, astronomers can decompose the recovery into multiple components, each with its own timescale. Some Vela glitches show at least 3 distinct recovery timescales: a fast one of a few hours, a medium one of a few days, and a slow one of weeks to months. Each of these timescales presumably corresponds to a different region of the star or a different physical process re-establishing equilibrium after the sudden disturbance. Not all pulsars that glitch behave like Vela. Some pulsars show what astronomers call anti-glitches, sudden decreases in spin rate rather than increases. These are much rarer than normal glitches and are associated primarily with magnetars, neutron stars with extraordinarily strong magnetic fields. An anti-glitch is the opposite of a regular glitch. Instead of the star suddenly spinning faster, it suddenly spins slower. The mechanism behind anti-glitches is thought to be different from the superfluid vortex unpinning that drives regular glitches. Anti-glitches might involve a sudden rearrangement of the star's magnetic field, which changes the external torque on the star and causes it to lose angular momentum rapidly. But anti-glitches are rare enough and poorly understood enough that they remain a frontier of research. There's also a phenomenon called timing noise that's related to, but distinct from glitches. Timing noise is a low-level, continuous wandering of the pulse arrival times away from the predictions of the timing model. Unlike glitches, which are sudden and discrete, timing noise is gradual and stochastic. It shows up as slow, irregular drifts in the timing residuals. Young pulsars tend to have more timing noise than old ones, and pulsars that glitch frequently also tend to have more timing noise. Some researchers think timing noise and glitches might be related phenomena, different manifestations of the same internal dynamics. Perhaps timing noise is the cumulative effect of many tiny, unresolvable glitches, so small that they blend together into a continuous wandering. Or perhaps timing noise reflects ongoing, low-level angular momentum exchange between the superfluid and the crust that never builds up to a full glitch. The relationship between glitches and timing noise is still an active area of research. Let me give you a sense of what it's like to actually discover a glitch, because the human experience of the discovery adds something that the numbers alone don't capture. Imagine you're an astronomer monitoring a pulsar. You've been observing it for years. You know its period to 15 decimal places. You have a timing model that predicts every pulse to within microseconds. You observe the pulsar every few days or every week, download the data, process it, and check the timing residuals. Month after month, the residuals are flat. The pulsar is doing exactly what you expect. It's almost boring. The data confirms the model every single time. You start to take the stability for granted. Then, one day, you process a new observation, and the residuals aren't flat anymore. There's a discontinuity. The recent data points are offset from the model's prediction. The pulsars are arriving earlier than expected. You check for errors. Maybe the telescope had a problem. Maybe the clock at the observatory drifted. Maybe you made a mistake in the data processing. You rerun the analysis. You check the observatory logs. Everything looks fine. The offset is real. The pulsar's period has changed. You look at the size of the offset and your stomach drops a little because you realize what you're looking at. This isn't a measurement error. This isn't instrumental. This is the pulsar itself. Something happened inside that neutron star. Something shifted. The crust sped up. Angular momentum was transferred. A process that might have been building for months or years just released itself in an instant. And you're seeing the aftermath in your data. There's a moment of genuine awe in that realization. You're sitting in front of a computer screen, looking at a column of numbers, and those numbers are telling you that a dead star nearly 1,000 light years away just did something unexpected. Something physical happened in the interior of an object so dense that a teaspoon of it would outweigh a mountain. And you know about it because photons that left that star hundreds of years ago, carrying the precise timing signature of its rotation, arrived at your telescope and told you. The star communicated its internal upheaval to you across hundreds of light years of empty space, encoded in the arrival times of radio pulses. That's extraordinary. And then the work begins. You alert your colleagues. Other observatories around the world start monitoring the pulsar more intensely to track the recovery. You measure the size of the glitch. You characterize the initial frequency jump. You watch as the spin-down rate changes. You fit recovery models with multiple exponential components, trying to extract the timescales. Every data point in the recovery phase is precious because it carries information about the internal structure of the neutron star. The way the star relaxes back toward its pre-glitch state tells you about the coupling between the crust and the superfluid, about the viscosity of neutron star matter, about the pinning forces that hold superfluid vortices to the crystal lattice. Every glitch is an experiment that nature runs for you, and the recovery is the result. Over the decades since that first detection in 1969, glitch observations have gone from surprising curiosities to a systematic field of study. There are now glitch catalogs, databases that compile every observed glitch from every pulsar, recording the glitch epoch, the fractional frequency change, the change in spin-down rate, the recovery timescales, and the persistent offsets. These catalogs contain hundreds of events, and they're growing every year as more pulsars are monitored and more glitches are detected. Statistical analyses of these catalogs have revealed patterns. Pulsars with higher spin-down rates tend to glitch more often and with larger glitches. There's a correlation between the rate at which a pulsar loses rotational energy and the rate at which it produces glitches, as if the glitches are a direct response to the spin down. The star slows down, stress builds up inside, and periodically that stress is released in a glitch. The faster the star slows down, the faster the stress accumulates, and the more frequently glitches occur. There's also evidence that glitches in some pulsars are quasi-periodic. The Vela pulsar's glitches occur roughly every 2 to 3 years. Not exactly periodically, there's quite a bit of variation, but there's a characteristic timescale. This suggests that whatever reservoir of angular momentum is being tapped by the glitches takes about 2 to 3 years to refill after each event. The superfluid stores up angular momentum as the crust slows down, and after 2 to 3 years, enough is accumulated to trigger the next glitch. It's like a geyser that erupts at semi-regular intervals because it takes a certain amount of time for the underground water to heat up and pressurize enough to blow. But other pulsars show no such regularity. Their glitches appear to be randomly distributed in time, with no characteristic waiting period. Some pulsars go decades between glitches. Others have bursts of activity followed by long quiet periods. The diversity challenges any simple model and suggests that the conditions inside neutron stars vary significantly from one star to another. What ties all of this together? What makes glitches a coherent phenomenon rather than just a collection of curiosities is the central observation. A pulsar that should be spinning down smoothly and predictably instead shows sudden, discrete jumps in its rotation rate. The jumps are too fast to resolve, happening in seconds or less. They are followed by complex multi-time scale recoveries. They leave permanent changes in the rotation state. They are correlated with the pulsar's spin down rate and age, and they occur in hundreds of pulsars across the galaxy, confirming that this is not a quirk of one or two unusual objects, but a fundamental feature of neutron star physics. Something inside these stars is storing angular momentum and releasing it suddenly. Something is building up and snapping. The observational evidence is overwhelming and detailed. We know what the glitches look like from the outside. We know their sizes, their timescales, their statistics. We know which pulsars glitch and how often. We know what the recovery looks like. What we need now is the physics, the mechanism, the answer to the question that has driven pulsar research for over 50 years. What is actually happening inside the star when it glitches? What physical process can store angular momentum slowly, release it suddenly, and produce all the observational signatures we've measured? That question takes us into the deep interior of a neutron star, into a realm of superfluids and crystal lattices and quantized vortices and nuclear forces. And the answer, or at least our best current understanding of it, is one of the most remarkable stories in modern physics. So, what is actually happening inside the neutron star when it glitches? What physical mechanism can store angular momentum slowly over months or years, and then release it in a fraction of a second? To answer this, we need to go inside the star. And what we find in there is one of the most extraordinary environments in the known universe. Let's start with the structure. A neutron star is not a uniform ball. It has layers, each with radically different physical properties. The outermost layer is a thin atmosphere, perhaps only a few centimeters deep, made of ionized gas so hot it glows in X-rays. Beneath that is the outer crust. This is a layer of solid matter, roughly half a mile to a mile thick, composed of atomic nuclei arranged in a crystal lattice with a sea of electrons flowing between them. The nuclei at the very surface are mostly iron, the same element that caused the core collapse in the first place. But as you go deeper into the crust, the pressure increases and the nuclei become more and more neutron rich. They absorb electrons, converting protons into neutrons, becoming exotic isotopes that don't exist naturally anywhere on Earth. Isotopes so overloaded with neutrons that they would be wildly unstable under normal conditions. But here, under pressures of billions of tons per square inch, they are held together by the immense weight of everything above them. And at the deepest layers of the crust, just above the boundary where neutrons begin to drip free, matter takes on shapes so strange that physicists have given them names borrowed from an Italian restaurant. This is called nuclear pasta. At these depths, the competition between the strong nuclear force, which wants to pull nucleons together, and the electromagnetic force, which wants to push protons apart, produces structures that are neither fully spherical nuclei nor fully uniform nuclear matter. Instead, the nuclear material distorts into elongated rods, like strands of spaghetti. Go deeper, and the rods merge into flat sheets, like lasagna. Deeper still, the sheets develop cylindrical holes, called anti-spaghetti or bucatini. And even deeper, the holes become spherical bubbles in a sea of nuclear matter, called Swiss cheese or gnocchi, depending on who you ask. These pasta phases exist in a narrow band of density, perhaps only a few hundred meters thick, sandwiched between the normal crustal lattice above and the uniform nuclear fluid below. But this narrow band may be enormously important for glitches. The mechanical properties of nuclear pasta are different from those of the regular crystal lattice. Pasta phases might be far stronger than ordinary crustal material. Some calculations suggest that nuclear pasta could be the strongest material in the universe, with a breaking strain about 10 times higher than conventional engineering materials like steel. If this is correct, pasta layers could affect how stress builds and releases during starquakes. They could also affect how superfluid vortices pin and unpin, because a vortex threading through a sheet of lasagna-shaped nuclear matter interacts very differently than one threading through a lattice of spherical nuclei. The pasta phases might act as barriers or channels for vortex motion, altering the dynamics of the avalanche in ways we're only beginning to model. We cannot observe nuclear pasta directly. No telescope sees inside a neutron star's crust. But the existence of these phases is predicted by multiple independent nuclear physics calculations, and their potential influence on glitch physics is one of the most active frontiers in neutron star theory. Keep going deeper, and you reach a critical boundary. It's called the neutron drip point. At this depth, the pressure is so extreme that neutrons begin to leak out of the nuclei. They literally drip free, escaping the nuclear surface and forming a gas of free neutrons that fills the spaces between the remaining nuclei. Below the neutron drip point, you're in the inner crust. Here, the matter is a bizarre mixture. Nuclei still exist, still arranged in a lattice, but they're swimming in a sea of free neutrons. And those free neutrons, at these densities and temperatures, form a superfluid. This is the key. The inner crust of a neutron star contains a neutron superfluid, coexisting with a solid crystal lattice. Two completely different states of matter, one rigid and one frictionless, occupying the same physical space, and they can rotate at different rates. The crust, being solid and connected to the magnetic field, feels the breaking torque of magnetic dipole radiation. It slows down steadily. The superfluid, being frictionless, doesn't feel that torque directly. It has no viscosity. It doesn't care what the crust is doing. Left to its own devices, it would just keep spinning at whatever rate it was spinning when the torque started. It would resist slowing down because there's nothing to slow it down. No friction, no drag, nothing. But the superfluid isn't completely disconnected from the crust. It interacts with it through the quantized vortices. Remember, a superfluid can't rotate as a uniform body. Remember, the superfluid rotates through quantized vortices, tiny threads of circulation, each carrying a fixed amount of angular momentum. The more vortices the superfluid contains, the faster it effectively rotates. Fewer vortices means slower rotation. Now here's what matters for understanding glitches. For the superfluid to slow down, its vortices have to move outward, migrating away from the rotation axis toward the surface of the star. In a normal fluid, this would happen automatically. Viscosity would couple the fluid to its container, and both would slow down together. But in a superfluid, there's no viscosity to do this. The only way vortices can move is if some force pushes them. And here's where the pinning comes in. In the inner crust of a neutron star, the superfluid vortices interact with the nuclei in the crystal lattice. These interactions are nuclear in nature, arising from the strong nuclear force that holds nuclei together. In many cases, The vortex finds it energetically favorable to sit on a lattice site, to thread through a nucleus rather than between nuclei. When this happens, the vortex is pinned. It's stuck. It can't move outward because the nuclear interaction acts like glue, holding it in place. Now think about what this means for the rotation. The crust is slowing down because of magnetic braking. The superfluid is not slowing down because its vortices are pinned and can't move outward to reduce the rotation rate. As time passes, a difference builds up between the rotation rate of the crust and the rotation rate of the superfluid. The crust spins slower and slower. The superfluid keeps spinning at nearly its original rate, held there by the pinned vortices. The superfluid is rotating faster than the crust. There's a velocity lag between them. This velocity lag creates a force on the vortices. The spinning superfluid exerts a force called the Magnus force on each vortex, pushing it outward, trying to move it toward the equator. But the pinning force resists. The vortex stays put. The Magnus force pushes. The pinning force holds. As the crust continues to slow down and the velocity lag grows, the Magnus force on each vortex increases. The stress builds. The pins are under more and more strain. Each vortex is being pulled harder and harder by the superfluid's rotation, while the nuclear forces pin it to the lattice. At some point, the stress exceeds the pinning strength. The vortex breaks free, it unpins, and once it unpins, it moves outward rapidly, driven by the accumulated Magnus force. But here's what makes this catastrophic rather than gradual. Vortices don't unpin one at a time, at least not during a glitch. The unpinning of one vortex disturbs the local conditions, making it easier for neighboring vortices to unpin too. It's an avalanche. One vortex breaks free, which triggers the next, which triggers the next, and suddenly billions or trillions of vortices are unpinning simultaneously, surging outward in a cascading wave. As these vortices move outward, they transfer their angular momentum to the crust. The superfluid, by losing vortices from the interior, reduces its own rotation rate. It slows down, and the crust, receiving that angular momentum, speeds up. The spin rate of the crust increases. The pulse period decreases. The pulsar glitches. The whole process can happen extremely fast because the superfluid, once the vortices are free, responds on quantum mechanical timescales. The avalanche of unpinning, the outward rush of vortices, the transfer of angular momentum, all of it can occur in seconds or less. This is consistent with the observational constraint that Vela glitches happen in less than 12 seconds, and probably much faster. After the glitch, the system begins to recover. The vortices that moved outward are now in a new configuration. Some of them repin to the lattice at their new locations. Others remain free for a while, gradually coupling back to the crust through weaker interactions. As the vortices repin, the superfluid is once again locked to the crust, and both slow down together until the velocity lag builds up again, and the cycle repeats. The different timescales of recovery, hours, days, months, correspond to different regions of the crust where the pinning conditions are different. Regions where pinning is strong recouple slowly. Regions where pinning is weak recouple quickly. The multi-component recovery curves that astronomers observe in the timing data are like a map of the pinning landscape inside the neutron star. This is the superfluid vortex model of pulsar glitches, and it was developed over decades through the work of many physicists. The core ideas were laid out in the 1970s and 1980s by researchers including Alpar, Anderson, Pines, and Shaham. building on earlier work by Baim, Pethick, and Pines. It remains the leading explanation for pulsar glitches today. Not the only one, but the most widely accepted and the one that best accounts for the full range of observational data. But there's an older idea that deserves a mention because it was the first serious attempt to explain glitches, and it captures something important about the crust, even if it's no longer considered the primary mechanism for most glitches. The starquake model. The starquake model was proposed shortly after the first Vela glitch was observed. The idea is straightforward. A rotating neutron star is slightly ablate, bulging at the equator due to centrifugal force, just as Earth is slightly wider at the equator than from pole to pole. As the pulsar spins down, the centrifugal force decreases. The equilibrium shape becomes less oblate, more spherical, but the crust is rigid. It's a solid crystal lattice. It can't smoothly readjust to the new equilibrium shape. Instead, it maintains its old, more oblate shape for a while, sustained by the rigidity of the crystal structure. Stress accumulates in the crust, the difference between the shape the crust has and the shape it wants to have. Eventually, the stress exceeds the breaking strain of the crust. The crust cracks, it fractures, a starquake. When the crust cracks, it settles slightly toward the less oblate equilibrium shape. The star gets a tiny bit more spherical. Its moment of inertia decreases by a small amount. And by conservation of angular momentum, a decrease in moment of inertia produces an increase in rotation rate. The star spins up. It glitches. The starquake model is elegant and physically intuitive. Everyone can imagine a crust cracking under stress. It's like an earthquake, just on a neutron star. And it probably does happen. Neutron star crusts almost certainly do crack and settle from time to time. But there's a problem. The starquake model can't account for the large glitches observed in the Vela pulsar. The amount of ablateness change required to produce a Vela-sized glitch is larger than the crust can accommodate. The numbers don't add up. The crust would need to crack and settle repeatedly, but each crack can only relieve a small amount of stress, and the resulting spin-up is too small to explain what's observed. Starquakes might explain some of the smaller glitches, particularly in pulsars like the Crab, where the glitches are tiny. But for the big Vela glitches, you need something more. You need the superfluid. It's worth noting that the two mechanisms are not mutually exclusive. In fact, some researchers think they might be connected. A starquake, a crack in the crust, could trigger the unpinning of superfluid vortices. The sudden rearrangement of the crystal lattice during a quake would disturb the pinning sites, knocking vortices free and initiating the avalanche that produces the bulk of the glitch. In this picture, the starquake is the trigger and the superfluid unpinning is the main event. The quake provides the spark. The superfluid provides the fuel. This combined model is speculative, but it's an active area of theoretical research. Now, I want to be clear about what we know and what we don't. The superfluid vortex model is the leading explanation. It's consistent with most of the observational data. It explains the size of Vela glitches, the recovery timescales, the correlation between glitch activity and spin down rate, and the cumulative angular momentum budget. But it is not settled science. There are significant uncertainties. We don't know the exact pinning forces. The strength of the interaction between a vortex and a lattice nucleus depends on nuclear physics at densities we can't reproduce in any laboratory. Different theoretical calculations give different answers, sometimes by factors of 10 or more. This uncertainty affects predictions of how much angular momentum can be stored, how often glitches should occur, and how large they should be. We don't know exactly where the superfluid responsible for glitches resides. The inner crust is the most commonly cited location, but some models suggest that superfluid in the outer core might also play a role. The core of a neutron star, below the crust, is expected to contain superfluid neutrons and possibly superconducting protons. The coupling between these core superfluids and the crust is different from the coupling in the inner crust, and the physics is even more uncertain. Whether core superfluids contribute to glitches is an open question. We don't fully understand the trigger mechanism. What exactly initiates the vortex avalanche? Is it purely a matter of the Magnus force exceeding the pinning force at some critical lag? Or is there a trigger, like a starquake or a magnetic event, that kicks things off? Different models give different answers, and the observational data isn't yet precise enough to distinguish between them. And we don't know the full equation of state of neutron star matter. The equation of state describes the relationship between pressure and density inside the star. It determines the star's internal structure, its mass-radius relationship, and the properties of its various layers. Different equations of state predict different crust thicknesses, different superfluid properties, and different glitch behaviors. Constraining the equation of state is one of the biggest goals in neutron star physics, and glitch observations are one of the tools being used to do it. This is what makes pulsar glitches so scientifically valuable. They're not just curiosities, they're probes. Each glitch tells us something about the interior of a neutron star. The size of the glitch constrains the amount of superfluid involved. The recovery timescales constrain the coupling between the superfluid and the crust. The cumulative glitch activity constrains the fraction of the star's moment of inertia that participates in glitching. These statistics of glitch sizes and waiting times constrain the pinning forces and the dynamics of vortex avalanches. Every glitch is a window into physics that we cannot access any other way. And this brings us to the deepest reason why pulsar glitches matter. They teach us about matter at densities that exist nowhere else in the observable universe except inside neutron stars. The density inside a neutron star ranges from a few billion kilograms per cubic meter at the surface to several hundred quadrillion kilograms per cubic meter in the core. At these densities, matter behaves in ways that our best theories can only approximate. The strong nuclear force, the same force that holds protons and neutrons together inside atomic nuclei, governs the behavior of matter throughout the neutron star. But at the densities found in the core, the neutrons and protons might break down into their constituent quarks. The matter might transition from a nuclear fluid to a quark-gluon plasma, a state of matter that existed in the first microseconds after the Big Bang, and that physicists try to recreate briefly in particle accelerators, like the ones at CERN. Some theories suggest that the core might contain exotic states of matter like strange quark matter, made of up, down, and strange quarks in roughly equal proportions. If strange quark matter exists, it might be the true ground state of matter, more stable than ordinary nuclear matter. This would have profound implications for physics and cosmology. We cannot create these conditions in laboratories. The highest densities achievable in particle colliders last for tiny fractions of a second and involve volumes smaller than an atomic nucleus. Neutron stars sustain these conditions across a sphere 12 miles wide for millions or billions of years. They are the only natural laboratories where matter at supernuclear density exists in a stable, observable form, and glitches are one of the only ways we can peer inside and probe what that matter is doing. This is why hundreds of physicists around the world study pulsar glitches. Not because the jumps in rotation rate are intrinsically fascinating, though they are, but because those tiny jumps carry encoded information about the state of matter at the most extreme densities in the cosmos. Every glitch is a message. Every recovery curve is a map. Every statistical pattern in the glitch catalog is a constraint on the physics of matter in conditions we can never hope to replicate on Earth. Pulsar glitch research connects to some of the biggest open questions in fundamental physics. What is the equation of state of dense matter? How does the strong nuclear force behave at extreme densities? Does quark matter exist inside neutron stars? What are the transport properties of superfluid nuclear matter? How do superfluids and solids interact at nuclear density? These questions sit at the intersection of nuclear physics, particle physics, condensed matter physics, and astrophysics. Pulsar glitches provide one of the only empirical handles we have on any of them. New observational facilities are making glitch science more powerful than ever. More sensitive radio telescopes are discovering new pulsars and monitoring known pulsars with higher cadence and better time resolution. X-ray telescopes like NISA, mounted on the International Space Station, are measuring the sizes and masses of neutron stars with unprecedented precision, constraining the equation of state from a completely different direction. Gravitational wave detectors like LY-GO are sensitive enough that a sufficiently close or sufficiently large neutron star event could provide complementary information about neutron star interiors. The combination of pulsar timing, X-ray observations, and gravitational wave astronomy is creating a multi-messenger picture of neutron star physics that would have been unimaginable a few decades ago. The next generation of radio telescopes will transform glitch science. The Square Kilometre Array, currently under construction across sites in Australia and South Africa, will be the most sensitive radio telescope ever built. When it comes online, it will discover thousands of new pulsars, potentially increasing the known population by a factor of 5 or more. More pulsars means more glitches. More glitches means better statistics. Better statistics means tighter constraints on the physics. The Square Kilometre Array will also monitor known pulsars with far higher cadence than current telescopes, increasing the chances of catching a glitch in the act during the actual moment of spin-up, rather than discovering it hours or days later. If we can resolve the rise time of a large glitch, measuring exactly how many seconds or fractions of a second the spin-up takes, it would provide a direct constraint on how fast vortices can unpin and move through the crust. That single measurement would rule out entire families of theoretical models. On the gravitational wave side, future detectors might be sensitive enough to detect the gravitational radiation emitted by a glitch itself. A sudden rearrangement of mass inside a neutron star, the kind of event that a large glitch represents, should produce a brief burst of gravitational waves. These waves will carry information about the geometry of the event, about how much mass moved and how quickly. Information that radio timing alone cannot provide. Detecting gravitational waves from a pulsar glitch would open an entirely new observational channel, allowing us to see the event from the inside out rather than inferring internal behavior from the rotation of the surface. We're not there yet. Current detectors are not quite sensitive enough, but the next generation might be. And when that happens, A pulsar glitch won't just be heard, it will be felt. And there's something poetic about all of this. Here we are, on a small rocky planet orbiting an ordinary star in a quiet arm of one galaxy among trillions, pointing our telescopes at dead stars hundreds or thousands of light years away. We're listening to the ticking of cosmic clocks that were set spinning by explosions more violent than anything else in the universe. And when those clocks hiccup, when they skip a beat, we don't just notice. We measure the skip to within microseconds. We analyze its shape. We decompose its recovery into multiple timescales. We infer the properties of matter in the most extreme conditions nature can produce. We learn about superfluids that exist at temperatures of hundreds of millions of degrees. We learn about crystal lattices made of nuclei so neutron-rich they can't exist on Earth. We learn about quantum vortices threading through matter at densities where a teaspoon would outweigh a mountain range. A dead star glitches, and we understand the universe a little better. That's what a pulsar glitch really is. It's not just a timing anomaly. It's not just a blip in the data. It is the sound of a superfluid ocean inside a dead star suddenly releasing the angular momentum it has been hoarding for years. It is the snap of billions of quantum vortices breaking free from a crystal lattice made of matter that doesn't exist anywhere else in the universe. It is a message from inside an object so dense, so extreme, so far beyond anything in human experience that even our best theories can only approximate what's happening in there. And the fact that we can detect it at all, the fact that a sudden shift in rotation rate smaller than 1 part in a million can be measured across hundreds of light years of empty space, tells you something remarkable about human ingenuity. We built the instruments, we developed the mathematics, we created the theoretical frameworks, we figured out how to listen to dead stars and decode what they're telling us about the deepest layers of matter. A species that evolved to survive on a savanna, to track prey and avoid predators, to count the members of a small tribe. That same species is now timing the rotation of neutron stars to nanosecond precision and using the results to constrain the behavior of superfluid nuclear matter at hundreds of quadrillions of kilograms per cubic meter. So the next time you look up at the night sky, at all those points of light scattered across the darkness, remember that some of those lights aren't ordinary stars. Some of them are dead, collapsed, compressed to densities beyond imagination, spinning in the void, sweeping beams of radiation through space, ticking like the most precise clocks in the universe. And every once in a while, without any warning, one of them jumps. Something deep inside shifts. A superfluid releases its grip. The crust lurches forward. And an astronomer on Earth, sitting in front of a computer screen, looking at a column of numbers, notices that the clock skipped a beat. That's the story of a pulsar glitch. A dead star that suddenly jumps. And the reason it jumps is that it isn't really dead at all. Not inside. Inside, it's a churning, dynamic, quantum mechanical marvel. A place where matter exists in states we've barely begun to understand. A natural laboratory operating at conditions we will never reproduce. And every glitch is an invitation to learn more. We don't have all the answers yet. We may never have all of them. The interior of a neutron star is shielded from us by a crust of ultra-dense matter and hundreds of light years of space. We can't drill into it. We can't sample it. We can only listen. But listening has brought us remarkably far. From the first confused detection of a radio pulse in 1967 to the sophisticated glitch catalogs and superfluid models of today, We've gone from not knowing pulsars existed to understanding, at least in broad outline, the quantum mechanical processes happening inside them. That's less than 60 years of progress. Imagine where we'll be in another 60. The universe is full of dead stars. Thousands of them in our galaxy alone are pulsing, ticking, spinning in the darkness. Most of them will never glitch while we're watching, but some will. And when they do, we'll be listening, ready to catch the jump, ready to decode the message, ready to learn a little more about what matter does when the universe crushes it beyond all recognition. A dead star jumps, and we listen. That's science. That's wonder. And that's enough.